Okay, here we'll see simple LR, canonical LR, and LALR. Three types of parsers we'll see, and four types of tables we'll be seeing: LR0 table, LR1 table, CLR table, and things like that. The most prevalent type of bottom-up parser, whatever we have today, like Yak and all, it is based on the concept called as LR of K parsing, wherein L is left to right reading, R is rightmost derivation and reverse, right? Looking K symbols ahead, right? So this is how the today's LR parsing works. K can be 0 or it can be 1 till now. Whatever we have seen the parses which is existing today is either K is equal to 0 or K is equal to 1. Okay, and more complex things than LR parsing are CLR and LALR. These two also will be learning. Now the question is why we are moving on to LALR or LR parsers when we have a shift reduce parser. As we have seen, the conflicts are one reason. The other reason is LR parsers can be constructed to recognize virtually all programming language constructs for which context-free grammars can be written. So whatever the grammar you write, you can construct all the LR parsers for all those types of grammars. That is one of the reason, and it is a most general non-backtracking shift reduce parser because it's a table-driven parser which knows when to shift and when to reduce, and then it can detect syntactically errors as soon as it is possible. So it is good in recognizing errors. That's why, and the class of grammars which it covers is more than the LL class of grammars, because some of the ambiguous grammars also it handles, wherein LL cannot handle the left recursive and left factor grammars. Okay, these are the things why we move to LR parsing when we have shift reduce parser. Okay, before starting with the LR parser, we have to see some of the things which are related to this. The couple of terms which are used in the LR parsing. First one which we have to see is items. Okay, what are items? How to construct items, and how to construct the LR of 0 automata. So we'll look at some of the definitions called items. So the items are very important when you are making shift and reduce decisions. Okay, how does a shift reduce parser know when to shift and when to reduce? So this decision is made in LR parser by maintaining states. Like you have to construct a DFA. Using that, you maintain this. You decide on these actions. So each state on the DFA, it represents a set of items. Okay, states represent what happened now. States represent a set of items. In each state, we will have the set of items. Now, what is an item? We usually call in a shorthand form as items, but it is actually LR of 0 item. Okay, we directly call it as item instead of calling every time LR of 0 item, LR of 0 item. We just call them as a shorthand as items. So LR of 0 item of a grammar G, all of you make a note of this, of a grammar G. I'll explain what is it later once you write the definition. Is a production. Okay, it's a production. Item is nothing but a production of G with a dot at some position of the body or in the body. Okay, what is an item? Item is nothing but it's a production of G with a dot somewhere in the production body. So suppose I have a production like this, XYZ. Okay, it yields 4 items. So what does the definition say? It should be there somewhere in the production body. Okay, somewhere in XYZ. So what are the 4 items which it yields is A gives dot XYZ. Okay, A gives X dot YZ. A gives XY dot Z. A gives XYZ dot. So these are the 4 items which we have got from this production. So this is an item because as per the definition, you should have dot somewhere in the production body. So it is there on the leftmost side. And here the dot is after X. Here the dot is after Z. Here the before Z, and here it is after Z.
Ma'am, so the dot should be present
Hmm.
implicitly or explicitly?
Implicitly or explicitly means?
Ma'am,
If
like
you have to
in
say,
A gives XYZ, we don't have a dot, but like.
no, this is the grammar. A gives XYZ is the grammar G. Okay, so the item for this production is these 4. That is how you form the items. Okay.
Yes, ma'am.
So if you have a production like this, A gives epsilon, then the item is A gives dot. We don't have anything, so it is just a dot. Okay, that is how the dot of A gives epsilon works out. So an item indicates, it's nothing but the position of the parser. Okay, an item indicates how much a production we have seen at a given point in the parsing process. That is the thing. For example, if you take this, we are in the beginning of the parsing process. So if you think that this is a parser position in the parsing process, so the parser is yet to see a string which can be derived from XYZ. That is the meaning of this item. So accordingly, if you take this item, the meaning is parser has already parsed a string which can be derived from X, and it is yet to see a string which can be derived from YZ. That is the meaning. If you take this item, it has already seen a string which can be derived from XY, but it is yet to see a string which can be derived from Z. That is the meaning. Now, the meaning of the last one, it has already seen a string which can be derived from X, Y, Z. Now it is the time for reducing it to A, because we are there in a bottom-up parser. Okay, we have seen the body and it can be reduced to A. XYZ can be replaced to A. That is how it, so till here it can shift because it can see the strings. Now whenever it moves to the end, that means it has already seen the whole body. That means the stack has XYZ on it. Okay, so now there is the time that it should replace this XYZ with A, right? This is the meaning of how do you form the items for a given production. Now, one collection of sets of LR of 0 items is called as canonical LR of 0 collection. Okay, one set is explicitly called as canonical LR of 0 collection. Okay, it provides the basis for constructing the DFA that is used for making passing decisions, okay, whether to shift or to reduce. So this collection is the basis for each of the states in the DFA, whatever the items are there. This is the basis for that. Okay, such an automata is called as, wherein you have the set of items in each of the state is called as LR of 0 automata. Okay, LR of 0 automata, and it is the basis for constructing your passing table, wherein we have shift and reduce actions. All right, to construct the canonical LR of 0 collection for a given grammar, we define 2 things. So now from the item definition, we saw how the what is the meaning of the item, right? And one set, such set wherein you have dots in the body of the production is called as canonical set of, or canonical LR of 0 collections. Okay, and this is the basis for your LR of 0 automata. To construct this canonical LR of 0 items, we use 2 rules. Okay, the first rule is you have to augment the grammar. To we have to define an augmented grammar before we form this collection. I'll tell you how to define an augmented grammar. I think it was not there in PAFL. And we define 2 functions. It was there? Augmented grammar was there in PAFL?
No.
Okay. Okay, so to construct this canonical set of collections, what we do is we define 2 rules. One is we have to augment the grammar, and then we have to use 2 functions to get this collection. The 2 functions are closure and goto. Okay, so now I will define what is an augmented grammar. What is the meaning of an augmented grammar? It's pretty simple. It's very simple. You can make a note of the definition. What is an augmentation means? All of you. The first thing, augmented grammar. Okay. If G, write down. If G is a grammar with start symbol S, then G dash, the augmented grammar, for G is G with a new start symbol S dash and production S dash gives S. Okay, this is how you augment the grammar. So if G is a grammar with start symbol S, then G dash, the augmented grammar for G, is G with a new start symbol S dash and a production S dash gives S. So what is the purpose of this new starting symbol? Can anyone guess what is the purpose of this? You can think of a shift reduce parser. Okay, so the meaning of come again.
No.
Okay, so if you take this grammar, so how do you augment this grammar? The first step is the augmentation, right? So how do you augment this grammar with respect to this definition? You need to have a new start symbol which derives the starting symbol of the given grammar. So I will have the new start symbol as E dash, which derives E. Okay, so it is G dash is nothing but it is G with new start symbol. So whatever is there in G should also be there with the new production. E dash gives E. So rest everything remains the same. Now, what is the purpose of introducing this? Is a question. Why should we increase?
So my guess is that yeah, last time when we did shift reduce parser, so in the end, the last row had to contain the start symbol and dash, right? So in order for the machine to realize that we have reached that step, if we have like a separate production that is just non-terminal to non-terminal S dash to S, then somehow it will help the machine realize that we reached that last step. I think that's that.
Good. Your guess is partly okay. Partly okay. So all of you can write the RMD for this string given this grammar. Don't use this grammar. ID plus ID. So you start with E gives E plus T, right? So E plus T. You replace T with F. Then you replace F with ID. Then you replace this E with T. Then T with F. Then F with ID. This is right. I have written the RMD. Now, we know that our shift reduce parser will start with the last one, and each time I get these things, right sentences forms on the top of the stack. Now what happens is, what we did, ID1 and ID2, you can refer that table. We pushed ID1 on top of the stack, right? So ID1 was pushed. Then what we did? We reduced ID to F, isn't it? ID to F, then F to T, that is what we did. Then T to E, right? Now what is there on top of the stack? At this step.
E, ma'am. So it might like mistake it to be the end of parsing.
Aha, that's right. Because plus ID is there still in the input buffer. E is on top of the stack now. So now that is the starting symbol of the grammar, right? So it can stop parsing. So when the parser should stop is a question, because it will not know that whether plus ID is there in the input or not. Whatever is there on the top of the stack, it should decide on based on that. So now to explicitly show that if suppose after this E, because every time I'm reducing it to E, right? So here, this might come. So E plus T can be reduced to E, E plus T can come on top of the stack and it can be reduced to E. Whenever T is there, T can also be reduced to E. No, so explicitly show that whenever E is getting reduced to E dash, only then you stop the parsing process. To make sure that happens, we augment the grammar. What it does is it gives, it introduces a new non-terminal, which just starts the gives the production of to the starting symbol. So it doesn't change the grammar in any manner. Your grammar is not at all changed. The resultant grammar is the same, right? In any manner it is not changed. Only new non-terminal will derive the starting symbol of the grammar. Is it clear why we augment the grammar? This is very important.
Ma'am,
Yeah?
is there some way to deal with left recursion if the starting if the start production if it is left recursive, is this like a way to deal with that?
No, no. So, left recursive is still okay because we start with the string, right?
Okay.
So it won't be a problem. It won't be a problem for bottom-up parser. It is a problem for top-down parser because we start with the starting symbol. If it is, and we use LMD. So if it is left recursive, it is in that recursion loop itself. So we shouldn't have left recursion, left factoring, wherein the ambiguity is on the left hand side. Okay, since this uses RMD, we don't have a problem with the left recursion.
Good.
Ma'am, one doubt, ma'am.
Huh.
Ma'am, as you said that once it sees E, it can stop. It does stop. So that's the reason we introduce E dash. So like
No,
the ambiguity is still here.
no. It doesn't stop at. See, if I use this grammar, I have used this grammar. If I use this grammar, where will I start? I will start at E dash, right?
Yes, ma'am. Like
Huh.
you said the advantage of this, right?
Correct. So this T is getting reduced to E. So E will be there on top of the stack. Now, according to this grammar, it has reached the root, right?
Yes,
If I
ma'am.
don't
That's what I
augment
was
it.
saying.
Huh. So whenever
So,
the whole thing E is getting reduced to E dash, then it can stop.
ma'am, but like it can reduce it to E dash itself. So
Huh.
then
So
it will
whenever
stop
E
here.
dash is on top of the stack,
No,
it
ma'am.
halts.
Like I was saying, if E gets reduced to E dash in the middle of the production.
Where? How? Where do you have?
Okay, fine. Yes.
Yeah, you don't have anywhere. Either it is T getting reduced to E plus T getting reduced to E. Only at the top you will have this. Otherwise, you don't have. That's why we augmented. Okay?
Like what I was saying is, the parser might get confused and substitute the production E dash derives E. So replace E with E dash.
No. No. No, you won't get that.
Okay,
T
ma'am.
to E. Okay. You will see in the parsing table. When we construct the parsing table, no, you will see how, because we still have to see the automata itself. So you mean to say from E to E dash it will do.
Yes, ma'am.
Okay. So in the construction of parsing table, it will be more clear how augmentation helps. Okay. This is the main purpose behind, when E is getting reduced to E dash, then it is the explicit halt. Okay, but when to shift and when to reduce and which production to apply, everything is table driven. Okay, so it won't get confused, in that case. But if I consider E as the starting symbol, then there is a confusion because E plus T can also be reduced to E, T can also be reduced to E. So there is a confusion here. So to avoid that, we have this production. Okay. But shift and reduce are definite when to use and how to use. There is no confusion in shift and reduction actions. So the second thing is, once we augment this grammar, we need two functions to construct the canonical set of collections of items. The first is the closure and then is the goto. So we'll see in this class the closure function, okay? Because it will take some time. Closure, how to construct the closure. All of you can make a note of this. I will just write the definition. Closure of item sets. I have uploaded the book as well in your course material, the PDF of the book, if you don't have it, for your reference. Now the closure, how do we derive the closure is, if I is a set of items, write down please, for a grammar G, okay, then, so if I is a set of items for a grammar G, then closure of I is the set of items constructed from I by two rules. Okay. So if I is a set of items for a grammar G, then closure of I is a set of items constructed from I by two rules. What are those rules? First one, initially add every item in I to closure of I. So whatever is there in I, the items, you have to add that to the set. The second rule is if A derives alpha dot B beta is enclosure of I and you have a production from B, okay, as B derives gamma is a production, then add B gives dot gamma to closure of I if it is not already present or if it is already not already there. Okay, and one more line you have to write down here. Apply this rule until no more new items can be added to the set. Okay, until no more new items can be added to the set. So how do you form the closure? You form the closure if I is a set of items for a grammar G, then closure of I is nothing but is the set of items constructed by constructed from I by two rules. The first one is whatever the set is given for closure of I, whatever is there in I, you have to add that initially to the set. Okay. Once you add that to the set, then you have to apply the second rule. What is the second rule? If at all, if you have A produces alpha dot B beta, that means after the dot, if you have a non-terminal and that non-terminal has some production in the given grammar, then you have to add that production with the dot at the leftmost side to the set if it is already not there. If it is there, then no need to repeat it again. And then again, you have to check after the dot if there is a non-terminal, then it has a production in the grammar, then you have to add that also. So that is the meaning of this. Apply this rule until no more new items can be added to the set. So I'll take an example. It will be easy for you to understand. Let us keep that augmented grammar as it is. Okay, this is the augmented grammar because this is the first step before we start with the closure. So if I is equal to E dash gives dot E, okay, then closure of I is what? We have to find out that using these two rules. I is E dash gives dot E, okay, and what is the closure of I? Now to form the closure of I, use these two rules. All of you try to write. What does the first rule say? Initially add every item in I to closure of I. So what is the initial item? It is initially add whatever is given. Okay. Now, once you add this, after the dot, I have E, which is a non-terminal and it has productions. Okay. So apply the second rule, alpha dot B beta. So B is nothing but a non-terminal here.
अच्छा वो नहीं था उसका वो मार्क्स हुआ
Manas?
sorry ma'am I unmuted by mistake.
Answer the question. Manas, answer the question. What was the question? he will abscond now. After the dot, I have E, right? So after the dot, I have B in this role. B has some productions, so E has some productions. I have to add those productions with the dot on the leftmost side. So tell me the production which I have to add.
E
I have to
gives
add
dot E
E plus D, then
dot
E gives dot T. That's right. Okay, understood. Now you take this production because I have to apply this rule until no more new items can be found. So this is done. After the dot E was there, E had some production, so I added those productions with the dot on the left hand side. Now I have this production. I have to check this. After dot, I have E, right? E's productions, the items are already there. So if no more new items can be added to the set, okay? So I need not write it again. Here, if you take this production, after dot, what I have? I have T. And their items are not there in the set, right? Because T has some productions. So how do you add them? You have to add
dot T star F and dot F.
Yes, very good. Now follow the same thing. I have to see from T. So this is a new item which I have added. After dot, I have T. T's productions are already there. Then it is fine. I need not add it. After dot, I have F. F's items are not there. So what I have to do? I have to add F's production as well with the dot.
Ma'am,
Okay.
the production of Fs are non-terminals now. Should we add them?
Terminus.
No, the rule is if it is B and B derives R. B is not, if here B is not at all, I mean,
No, we are
bracket
still
is
here.
non-terminal, no, is what I'm telling.
Yeah, but there is no rule saying gamma can't be a non-terminal.
Gamma is a set of strings. So it can be a combination of terminals, non-terminals together. Right? Okay.
Can you like give us an example where the dot is somewhere in the middle in any production?
Yeah. I will give that. Don't worry. So let us complete this set first. Okay. So F, according to this, after dot, I have a non-terminal. So non-terminals items are not there. I will include the productions of that non-terminal with a dot on the left-hand side. Now you check after the dot, I have a terminal. Okay. So it obviously doesn't have a production. After the dot, I have a terminal. So it doesn't have a production. So I stop here. So this is the complete set for closure of I, where I is E dash gives dot E. Understood? Okay. Now I will give you the second question. You have to do it.
Ma'am, like in square brackets is the set, in the flower brackets is the set notation. So like what's there in the square? Like the production has to be present in the square bracket, or like is it a defined notation of saying? Just asking.
Why do I have two pens in brackets there?
That is how it is written.
So if there are two productions in the set, each production is in square brackets.
Yes. Okay. I will write it here. So if I give E gives, T is one production, and T gives, yeah, now you can do it. This is I.
Ma'am, also ma'am, like the dot is the significance of an item, right? So
Yes.
like what does dot denote actually? It's like just says that it's an item or something?
No, that's what. Dot represents the position of the parser in the parsing process.
Okay.
Where exactly the parser is in the parser.
So yeah, as you said earlier, a production can have as many like depending on the characters present, it can have those many items.
But only one dot.
Yes, ma'am.
So with respect to this, what is the meaning of this? That means the parser has already seen a string derivable from T and a star. Now it is expecting to see either open brackets E or ID from the next non-terminal. That is meaning.
Okay, so like to be told in an generalized way, so like every position of a parser, we are taking that part as an item and then analyzing it.
Yes.
Ma'am, one more thing, ma'am. So given that E gives E plus dot T is in the closure set, and we need to take the productions of T now, do we take even the production of T that is there in the closure set?
Yes, because the dot will be there in a different position, right?
Okay, ma'am. So,
Yeah, it
then
should be exactly same. Then we don't add it.
got it.
Hmm. That's why I've given this. Try this closure of I. I will write here for this question. I'm writing here the answer so that these rules are there. So initially, what you have to add? You have to add whatever is there in I. Okay, according to the first rule. So I take E gives E plus dot T and T gives T star dot F. Okay, initially it is there in the set. Now take the first one. After dot, I have a non-terminal and its productions are not there. It has to be same. Remember that. So T gives dot T star F and T gives dot F. See, even though this one and this one looks similar, the dot position is different. Okay, now there is a this thing. So let us finish this. I'm considering this now because of this dot T. I've written these two. Now you take this one, it's already there, right? These productions are already there with the same position of the parser. Now if you take this production, if productions are not there, so I will have to add fks id. Okay, now after dot I have a terminal. Here there is a dot. After dot I have id. Both are terminals, so no further items can be derived. Now this is over. Take the next one which is there in the I. Now after dot I have f. F productions are already there, so this is the set. Understood? Got an idea?
Yes,
How,
ma'am.
yeah. How to draw the closure? You want me to give one more example for you to draw?
Yes, ma'am.
Okay. So I can be F gives, yeah. Closure of I, find out. Of course, the algorithm in the, algorithm, as in I have given in steps, you can refer the book for the proper algorithm structure for closure and item. I will give it in the steps so that it is easy instead of generalizing in the notations of algorithm itself. It will be easy for you to understand here with the respective step. Then if you read the algorithm in the book, you will be able to understand it more properly. That is my idea. So how do you write this?
So, like, we begin with the E production. So,
Uh,
E gives dot E plus T.
you have to begin with this.
Yes, ma'am. That will be there
Hmm.
in the closure. I was talking about the next step, like
Hmm.
step 2 onwards.
Hmm. So step 2 onwards, all these things will be there in the set, isn't it?
Yes, ma'am.
Only instead of the first e dash gives dot e, you will have f gives brackets dot e. That is the only difference. Okay, understood. Now this closure is divided into two different sets called as kernel sets and non-kernel. I mean kernel set of items and non-kernel set of items. So I'll just give you the definitions. These are important because with respect to generation of the items, because for each state we have to generate the set of items, right? So whatever the items we have defined here is broadly divided into kernel items and non-kernel items. What is kernel items is, it is nothing but the initial item, that is s dash gives dot s in the grammar G, and all items whose dot are not at the left side. Okay, those are called as kernel items, not at the left side. Like this one is a kernel item, this one is a kernel item. Okay, and e dash gives dot e is a kernel item. This is the only where you have on the leftmost side the dot. Only the exception. That's why it is explicitly given in the definition. So the rest of the things are non-kernel items, wherein you have the dot at the leftmost side, and except s dash gives dot s. So all items, I'll tell you the significance why we divide them into these groups. With their dots at the left end side, except for s dash case dot s. Is it clear what are kernel items and what are non-kernel items? Now, each state we maintain this set, right? So you will have a combination of kernel items and non-kernel items depending on how do you derive the closure. Okay, what comes in closure of I? Now, can I generate non-kernel items from kernel items if I have kernel items?
Ma'am, I had one doubt. Like in kernel items, uh, the dot has to be on the extreme left or just the left side?
Left hand side, it is the beginning like this.
Okay,
And
so
all items whose dots are not
yes,
at this side, that means like this, it shouldn't have this item. This is not a kernel item. This is not a kernel item. All these are not a kernel items. Only these two are kernel items here. And this one, the starting one, is a kernel item. So what could be the significance of, with respect to the memory and the states are concerned? See, every state will apply this closure function to derive the items, okay? Because I have already told you each state is a set of items. Now, when I'm defining that set of items, I need to, store them somewhere, right? The DFA has to be stored to make the shift and reduce decisions. Now, when I'm designing this DFA, I need the set of items. Now, using the kernel items, I can, generate the non-kernel items. Do you agree with me? Because I have dot T. This is a kernel item, and T is whatever I have included in the set. I will throw them away. I will not store them. I'll apply the closure on this. I can easily get the non-kernel item related to T, but it's not possible to get the kernel item because we don't know the position of the parser for till where it has reached in this particular state. To do that, I have to store this somewhere, the kernel items. I can easily get the non-kernel items, but it is difficult to get the kernel item. That's why it is easy for me with the memory constraint. I can store only the kernel items and throw away the non-kernel items, apply the closure on the kernel item to get the non-kernel items wherever it is required. Okay, that's why we divide this kernel items into, these item sets into kernel and non-kernel. Understood why it is required?